Welcome back. Today we will be talking about the concept of continuity, and this is a Kuta software worksheet. So as you can see in the first problem, it is a piecewise function. We have two different domains, x is less than 1 and x is greater than or equal to 1. So if you look at the graph, we have the open circle at 1, so it is negative infinity to 1, and then we have a closed circle at 1 as well, so 1 to infinity. So two different graphs because it is a piecewise function and it is a one is open and one is closed. For the second problem, the the closed circle, that is just a coordinate, so we will not include that. In this, we can write the interval as negative infinity to 5 union 5 to infinity. That is just the closed dot, it is just the coordinate. For question number 3, so what is going on in here? We have the open graph and the lower function is the closed. So if I have to graph this, we can graph like this, and then this is for the second graph. F of x is equal to 0 when x is greater than or equal to 2. For the open, we are looking for a coordinate. Again, when we are looking for the graph, it should have the open circle because the top graph, it has the open circle, and then it is a jumped discontinuity, and I can write the interval notation as negative infinity to 2 union closed interval 2 comma infinity. Remember, when you write the interval for the infinity and negative infinity, it is always open circle. Question number 4, it is a rational function, so it is a removable, and I can factor it. If you factor the numerator, it is a quadratic. You will get x minus 2 times x plus 1, and at this point I can cross off x plus 1 from the numerator and denominator. When you cross off x plus 1 from the numerator and denominator, then this x is equal to negative 1. It defines a hole at that point. And now we are left with only x minus 2, that is a linear function, and we can easily graph the linear function x minus 2, but keeping that thing in mind that at x is equal to negative 1, it will be a hole. So that means we will assign an open circle in the line. So carefully, it will be an open circle that defines the hole. And then I can extend the graph because it is just a linear x minus 2. This is what the line we are looking for. Let's sketch the line now. And this is your lovely graph, nice and ready. And we can write the interval negative infinity to negative 1 because it has a hole at negative 1, and from negative 1 to infinity. Right, let's quickly go to question number 5. Yes, keep this thing in mind that x minus 2 is a linear graph. So number 5, again, it has a numerator and denominator. And with this, we can say this is an essential discontinuity because I cannot factor it further, right? So if I put denominator equal to 0, you will get the x value, and that x value is nothing but the asymptote at x is equal to negative 2. So that implies there is a discontinuity at this point. And then we can write our notation. So first write that it has a discontinuity at this point, which is x is equal to negative 2 because it is an asymptote. Asymptote implies that a dotted line where the graph will try to reach, but it will never touch the line. So this is my notation or the interval notation for this problem number 5. Number 6, again, it is a piecewise function. And with this piecewise function, we can look for, we have a quadratic, and then on the top, it is a linear function. So we can try the direct substitution. So direct substitution in the first function, that is 0 minus 7 half, which is 7 half, negative 7 half. And if you apply the direct substitution in the second function, you will get negative 2. And here we go. We can say both values are not equal to each other. So there is a jump discontinuity at x is equal to 0. Jump discontinuity. And then finally, we can write the interval notation. Negative infinity to 0, union 0 to infinity. And provided all the interval notation, it is in the open brackets. Right? Number 7, I can see we have a quadratic and a linear, so we can factor it. And because we can factor it, it is a removable discontinuity. So once we factor it, I will get x minus 4 and x plus 3 over x plus 3. And as at this point, I can cross off x plus 3 because that is common in numerator and denominator. And this x plus 3 will help us identify where will be a hole. So at x is equal to negative 3, the graph will have a hole. So quickly, interval notation, negative infinity to negative 3, open brackets, and negative 3 to infinity, open brackets again, because at x is equal to negative 3, we have a removable discontinuity, or we have a hole. Same thing with number 8. We can factor it because we have a quadratic and we have a linear. We can factor quadratic easily. So after factor, you will get x plus 2 times x minus 3, and then we have x plus 2 in the denominator. Oh, it is x plus 2 in the denominator, yes. So at this point, we can cross off x plus 2 and x plus 2, and that defines where there will be a hole in the graph. So there will be a hole at x is equal to negative 2, or this function has removable discontinuity at x is equal to negative 2. And this is my interval notation, nice and lovely. I hope it is making sense. Let's try number 9. And please don't forget to box your answers. Number 9. So in number 9, I cannot factor x squared. So what we will do, we will put denominator equal to 0 to find the vertical asymptote. And this is essential discontinuity. Right? That's what they are asking for. Determine if each function is continuous or not. So we will just say it has an essential discontinuity at x is equal to negative 2. That's it. Let's try number 10. Number 10, we have a linear and a quadratic, and the quadratic, I can factor it. And when you factor it, you can see you can cancel out numerator and denominator, and that cancel out x plus 1 expression will give you x is equal to negative 1 as the removable discontinuity, or we have a hole at that point, and also at x is equal to 2, we will have asymptote. So there are two things that are working here. We have essential discontinuity at x is equal to 2, and also removable discontinuity at x is equal to negative 1. Right? So this is a very interesting example because we have two types of discontinuity in the same problem. Number 11. Again, we have a quadratic, but I cannot factor it. So what we can do, we can use a quadratic formula. So when I use the quadratic formula, remember negative b plus minus radical of b squared minus 4ac divided by 2a. I got negative 1 plus minus radical of negative 3 over 2. So it is negative 3 over 2. That means it has an imaginary component to it. So no x value can make the denominator equal to 0. Right? So it will be continuous everywhere. Number 12. We cannot factor it, so it has a discontinuity at x is equal to 1, where it will have the asymptote, and that is why it has essential discontinuity. Now number 13, we have a piecewise function again. So if I do the direct substitution in the first function, you will get 0 minus 0 plus 3, which is nothing but 3. And the second function f of x is also 3. That means 3 is equal to 3. It is continuous. And how the graph will look like, because we have a quadratic and a constant, so it will be something like a U shape and with a line. This is how the graph should look like. It is continuous. Number 14. Again, we have a piecewise function. And if I graph it, it is a negative x squared. So it is U shape is downward facing because it is a negative square function. And it will have a hole at 1. Right? Because it says x cannot be equal to 1. So it will have a hole at 1. So removable discontinuity at x is equal to 1. Removable discontinuity. Clear? Number 15. There can be many ways to answer it. But, so they have given us the factor at as x is equal to 1, 2, and 3. So the simple way I would like to answer it is just writing it in the denominator as x minus 1 times x minus 2 times x minus 3. That's it. For number 16, you need to have an understanding of the basic trig functions, and they are asking for what types of discontinuities are there. So we can write for the continuous, the sine and cosine, they are continuous function, right? They oscillate. For the not continuous functions, we have the other functions, for example, secant, cosecant, tangent, and cot function. They are in the category of not continuous function because, you know, a secant and cosecant, they jump, right? And the tangent and cotangent, they have the asymptotes. Bye-bye. Thank you for watching.